Okay, so we're looking at inequalities again, but this time we have combined functions. Essentially, we have two different functions, and the question is asking us to find, without graphing, because if we were to graph both, just quickly, one of them probably does this, and the other one does something like this. So you can pretty obviously see that this guy is greater between these two intervals, or that's when g at x is greater, actually, and f at x is greater at the other points. But how would we solve this algebraically? Well, we essentially plug in our function for g at x. So we'll plug this in for our f at x, not g at x, sorry. And what we have for g at x, we'll plug in this function here for it. So we're not quite setting them equal to each other, but setting them into the inequality. So we have x cubed plus 8x squared minus 11x minus 12 is greater than negative x squared minus x plus 12. Okay, so again, this is kind of like this is our f at x is greater than, and this being our g at x, okay? Essentially, you create another function from them. The goal is to set them equal to 0, just like we had done with other inequalities, and depending on when they're graphed, their intercepts are where they're going to cross each other. Okay, so when we set it equal to 0, again, if we have a function like this and like this, we don't exactly know how they're going out, but our points when they cross each other are when the two will be equal to 0, essentially when they're neutral, when they cross each other. Okay, they cancel each other out, you could say. So we're going to set that equal to 0, not quite equal to 0. We'll kind of have it as 0 is greater than. That's the idea. So what we want to find out is when we're greater than 0, and again, that would be, sorry, our g at x is our cube, or our f at x is our cube. So the idea being, when are we here, and when are we all the way out here? Those are our ideas. Okay, so let's put it over to 0. So in other words, I'm going to move everything to the other side of the equation. Okay, so when I do that, this middle, or this balance of the equation, is going to shift over a little. So 0 is greater than negative x cubed. Okay, and then negative x squared, and this becomes negative 8x squared. Does that make sense so far? Yeah. I'll underline everything in red that we are moving. Okay, and the blue were the original equations. Negative x, that's blue, and then positive 11x, that's our red, and then finally positive 12 is our blue, and positive 12 again is our red. So we moved everything to the other side. The inequality didn't switch because we didn't multiply or divide by any negatives. So we're going to combine our like functions now. So we have 0 is greater than negative x cubed. Okay. Combine these two functions, gives us negative 9x squared. This gives us positive 10x plus 24. Okay. So we have a cubic function. Okay. So we want to, just like before, find what we consider our x-intercept. So instead of being a greater than sign, we kind of go back to that equal sign. When are we equal to 0 is what we're looking at. And we're going to have to use our long or synthetic division, right? So we first need to find an interval that will make everything 0, something that will factor out of this. What I might do is, okay, so I kind of cheated and used a program, but like I said, the way we would have done this is we would have discovered 2 as our first factor, so either synthetic or long division, we could have had our x minus 2. Set up our long division, we would have had a new quadratic, whatever it was. We wouldn't have been able to factor this nicely, so we used quadratic formula and found these 2 values after. So I quickly did that so we didn't have to go through the process. So on a number line, we want to represent this. Okay, these are our x-intercepts. In other words, of our new function, because this is a completely new function, right? It didn't have really, it does have to do, but it's not identical to these at all when graphed. So when graphed, this is really different. Let's do quickly a rough graph. Oops. Our x-intercepts, one is at negative 9, negative 9.7. Another one's at negative 1.2, and the other one's at a value of 2. And because this is a negative cubic function, it's going to come from above, okay, come back up, and then head down. Does that make sense to you? Okay, so we know we have this relationship. And really what that means is we were looking, okay, we were looking for when it was less than 0 or when 0 was greater than that. Okay, so when 0 was greater than that, well, 0 is greater, or y values are above the x-axis between here and anything to the left of here. Okay, we already know that by looking at it, but we should probably use our intervals to technically test it if they want algebraic proof of it. Okay, again, because they said they didn't really want us to graph it to solve, but we can use our graphing knowledge to kind of help us out. So we'll make our number line here, and we'll test our values. So again, with our number line, which is essentially our x-axis, we have negative 9.77. It goes on for a while, right? Negative 1.227. And I rounded there, which can be bad because that's not technically the right way to do it. But really, we just got to find values in between. So when testing, I wouldn't go, oh, let's use negative 1.2273. Like, that's ridiculous. I would just use something I know that's going to be between these values, right? So we can pick some numbers and quickly go through this. I know negative 10 is to the left of that. I know negative 2 is in between those. And I know 0 is in between there, and 3 is in between here. Okay, so these will be our numbers we'll plug into our equation to test, to make sure. And we're always looking for when we're less than. We're looking for when we're negative. So the question is, when are we negative when putting these intervals in? So we take our new equation, okay, the one that we built, and we plug it into that equation. Okay, so I'm going to call that equation h at x. Okay, so h at x is, and I could probably really nicely, I could technically put it into a factored form, because we haven't really talked about that, but we'll put it in our standard form here, is equal to negative x cubed, negative 9x squared plus 10x plus 24. So with our standard form, we plug in our 4 intervals here. Okay, so our first one being h at negative 10. And we'll quickly, we'll actually need all the values. So negative 10 cubed minus 9 times negative 10 squared plus 10 times negative 10 plus 24. Okay, this is 1,000, negative 1,000 times a negative positive 1,000. Are you okay with that?
Yeah.
This is positive 100 times 9 is negative 900. This is negative 100 plus 24. And when we work this all out, this is 1,000 minus 1,000, we get 24. So we get a positive value. Okay, so because it's positive here, that's not what we're looking for, right? So we know that's not it. We're looking for when it's negative, and assuming it's going to be a negative in here, which is exactly what we've drawn, but we're going to test it. Now, a fast way to test it, instead of keeping it in its standard form, because we have our x-intercepts, okay, a factored form of any polynomial is a being some coefficient, and then all of the actual x-intercepts, which are this value here, this value here, and this value here. Well, I can put them into a bracket with x by itself. If I just say x and positive 9.77, because we know if we set that equal to 0, it'd give us negative 9.77. X plus plus 1.227, because when we set it equals 0, same thing. And this one would be x minus 2. This can really help us find positive, negative, positive much quicker. The only thing is, the reason I say A is because it depends if it's a positive or negative polynomial. And that's the value we have to put in front. So because it's a negative polynomial, our A is going to be negative. So our actual h at x, when we go to plug this stuff in, will be negative. And then all of these values. And essentially what the negative does is it'll help us just figure out what's positive, what's negative, and kind of go from there. This will be our fast way of doing it. Okay? 227, and then x minus 2. So let's kind of cheat now. The next value we were going to do was negative 2. Great. So negative 2. If we were to plug negative 2 in, so we'll say h at negative 2, well, this stays as a negative. Okay, when I put negative 2 in here, this will become what?
Negative.
Well,
no, positive.
Yeah, that'll still stay positive. When I put it negative 2 in there, what will it be? Well, it'll be negative 2 plus this, negative. So it'll be a negative because the negative 2 is greater. Yeah. And then a negative 2 here will give us what?
Negative.
Yeah. So in other words, we have a negative times a positive, which is a negative, times a negative, which is a positive, times a negative. So essentially we get a negative value in the end. Okay, so I've kind of done that without actually using any of the values. Does that make sense?
Yeah.
Yeah? These two here become positive.
Yeah.
These two here become negative. Negative times positive, negative. Great. So this is negative. Exactly what we had said before. In that interval is when that function is greater. Okay. The next one we'll test is 0. So let's cheat our way with h at 0. We know our first interval is negative. 0 in here is going to be positive. 0 in here is going to be positive. And 0 in here is going to be negative. I don't know why I wrote a number, but okay. And we'll kind of put them together. These two become negative. Those two become negative. So together we get a positive. And you kind of get the idea, right? This will be positive. So therefore, this will be negative, which is exactly the interval we had said it would be. So when our x is between, so less than negative 1.227 and greater than, when x is greater than negative 9.7, and the other one is when x is greater than 2. Is greater than 2, okay? Does that make sense there?
Yeah.
Okay, so we've kind of gone through it using our trial and error method. We find our intervals and we just test our numbers in between. And this was our graph. These are technically all of the graphs. So get them all off here. These are the two functions, and this was our new black function that we figured out.